So we've just seen that this greedy algorithm is not a polynomial time C approximation for the TSP, for any C, right? And so this tells us something about greedy. It doesn't tell us something about the TSP. Okay, so it's a line of reasoning that I hope you're getting comfortable with in this class. But what do we know here? We know that greedy is not a C approximation for TSP for any C, right? Any finite C. Okay, but this doesn't directly tell us that there's a problem with the TSP. We've seen plenty of cases where a greedy algorithm doesn't work, but there's still some other algorithm that does. So the question is, does there exist a C approximation for the TSP? And the answer is not trivial. In fact, the answer is incredibly surprising. In fact, to me, it's incredibly surprising that we even have an answer to this question. But the answer turns out to be no. So no matter what, we can actually guarantee, subject to an interesting assumption we'll talk about in a second, but no matter what, we can actually guarantee that there is no polynomial time approximation algorithm for the TSP. And so what does this mean? What is this statement actually saying? This is actually saying that for any algorithm that you give me, I can generate an instance. In principle, I can generate an instance of the TSP where that algorithm performs as bad as I want. Okay, so this is a guarantee about all algorithms, right? This statement here, this simple no, is a statement that says every algorithm in existence, right? All of the infinitely many algorithms in existence, every single one fails to approximate the TSP, right? In a general sense. Okay, so how in the world can we possibly make a statement like this? And it turns out that the only way we can make a statement like this, at least in the current state of the art, in November of 2020, the only way we can make a statement like this is we can say that if P does not equal NP, then there exists no C approximation, right? So the idea here, and we'll expand on this, and I'll give you the full proof of this in a moment. The idea here is that if P does not equal NP, then no C approximation exists. For TSP, right? So this is a specific result for the optimization version of the TSP. This doesn't quite say that if P equals NP, then a C approximation exists. That can be a different topic for a different day. But we have this statement that begins if P does not equal to NP. So what you'll find if you ever dig deeper into CS theory is that this is an extremely important place that many CS theory papers start. And it's very common to say the results in this paper are assuming that P does not equal to NP. And if it does, the results in this paper are not valid. And sometimes, if P equals NP, it actually implies the opposite of the results in the paper. Not typically, but and not in this case, but it can go that way. And so this is a little bit of a strange thing, right? It gives us this idea that that a whole host of things that we think of as facts hinge on the answer to this question. Does P equal NP or does P not equal NP? And the fact that it's much more common in CS theory to say if P does, let's assume P does not equal NP, and then derive a whole bunch of stuff. And it's much more common to say that than the opposite. Is one of the ways of saying that the CS theory community tends to believe that P does not equal NP. So anyway, how would we do something like this? Well, to say if P does not equal to NP, then no C approximation exists for the traveling salesperson problem. So what would this argument actually look like? Well, it looks like the following. Let's take a problem that we know is NP complete and define a reduction from that problem to the TSP. right? So the problem that we're going to use is called the Hamiltonian circuit problem. So let's write HC to mean Hamiltonian circuit. Okay, so the Hamiltonian circuit problem, you may remember, is this question where I give you a graph, and this graph doesn't have to have weights on it. It doesn't even have to have all edges. In fact, typically it won't have all edges if this is an interesting instance. So I give you a graph, and I ask, is there a way to visit all of the nodes in this graph exactly once, and then return to where you start, right? Does there exist a Hamiltonian circuit of this graph? And that's the Hamiltonian circuit problem, right? So here's two graphs, for example. All right, this graph is a yes instance of the Hamiltonian circuit problem, right? The Hamiltonian circuit problem is NP complete, which means it's a decision problem. It's one of the fundamental NP complete problems. So there's an example of a graph that that does have a Hamiltonian circuit, right? What's the circuit? Well, it's just visit all the nodes in sequence, right? It's super simple, right? It is just the graph, right? And then here's an example of a graph that trivially does not have a Hamiltonian circuit, right? So it's a connected graph, but there's no way to visit all the nodes exactly once and then return to where you start, right? So this has to be no. Any way of any attempt to create a circuit here would have to visit this node twice, right? So there's no way to do this. So that's a no. So this is an example of the Hamiltonian circuit, like a yes instance and a no instance. And so what we'll do is we'll define a reduction, a particular polynomial time reduction from the Hamiltonian circuit problem to the TSP. And so what we're doing, notice, is we're reducing an NP complete problem to a problem that's not even a decision problem, right? The TSP, the optimization version, is not a decision problem. It's an optimization problem. But nonetheless, we can still define a reduction. So we'll define a reduction, a polynomial time reduction, right? The only kind of reduction that's interesting to us in this class. Reduction from Hamiltonian circuit to TSP, right? I'll give you the specific reduction in just a second here. But then what we'll do is we'll say that suppose we have a C approximation for the TSP, and then we'll use that C approximation and this reduction to show that if we had one, that C approximation would be a polynomial time algorithm for the Hamiltonian circuit problem. In other words, if we had a C approximation, then P would equal NP. We don't think P equals NP, so we think we don't have a C approximation, right? That's the way this argument's going to go. So we'll define, just to finish our sketch here, we define a polynomial time reduction from Hamiltonian circuit to TSP, and then we'll show that a C approximation for TSP would be a polynomial time algorithm for HC. Right? And of course, as part of that algorithm, we would use this problem reduction, right? The reduction from Hamiltonian circuit to TSP. Right? And what would that imply? That would imply that HC is in P, right? And we think this is false, right? This appears to be false, and so we're just gonna go forward, right? In other words, what we show is that if TSP is approximable, then P equals NP, right? What's the contrapositive of that? If P does not equal NP, then TSP is not approximable, right? So that's the approach here. So what's the reduction? So remember, what does a reduction do? A reduction converts instances of one into instances of another, right? So what we'll do is we'll say let G be a graph. So this is a graph that's phrased as a Hamiltonian circuit problem. And so now let's construct. We want to construct a new graph. G prime. and this will be an instance of the TSP. And so this graph here is instance of a Hamiltonian circuit, and this graph here is an instance of TSP. Okay, so here's how we'll do this. So we'll say for each edge in G, right? So if an edge appears between two nodes in G, then we'll put an edge in G prime with a weight of 1, right? So G is not a weighted graph necessarily, but G prime is a weighted graph because it's an instance of the TSP. So for each edge in the original graph, we'll define an edge in the TSP instance, in this new TSP instance, with a weight of 1. So put an edge in G prime with a weight of 1. Okay, and then for each edge in G, so for each edge, each edge not in G, right? And so what does it mean for an edge not to be in G? Well, it means that there's no link between those two nodes, right? So if we think back to the instances that I showed a second ago, what we're saying is this here, right? This node and this node do not have an edge connecting them. And so that's what we're talking about here, right? That is an edge that does not exist in this graph, okay? So that's an edge that doesn't exist in this graph. So for each edge not in G, we'll put an edge in G prime with a high cost, right? So rather than a low cost, we'll choose a high cost. Put an edge in G prime with a weight of, and let me get the number right, of C times N plus 1. And you say, what is C? Well, C is something that we'll reference to our approximation algorithm in a little bit. But C can be some large number, right? As large as we want. And N is the number of nodes. Okay, so what we'll end up doing is we'll define C. We'll say, suppose we have a C approximation for the TSP. Well, then we'll use that C approximation to solve the HC. So let me do a couple pictures here. So we've got two graphs. Suppose we've got this graph. Here we go. We'll do this. So here's G. I'll use my first example graph. And so notice this is a yes instance of the Hamiltonian circuit problem. And so what does our G prime look like for this? Well, our G prime says I've got 4 edges. So each of those edges are going to have a weight of 1. 1, 1, 1, 1. And then there's 2 edges that do not exist in my original graph. And so I'll give those edges a weight of C times N plus 1. And I'm going to draw this without any crossed lines. Cn plus 1, and then this is Cn plus 1. Okay. So what do we have? So if G, so let's analyze this instance first, and then we'll look at the next one. So if G has a Hamiltonian circuit, right? In this case, it does. Then what do we know about G prime? Well, then the optimal tour in G prime has a cost less than or equal to n. Okay, and why is that? Well, because suppose G has a Hamiltonian circuit. That Hamiltonian circuit is n edges long. Each of the edges that exist in this graph has a counterpart in this graph with a cost of 1. And so that means that we can just take this Hamiltonian circuit, which we know exists because this is a yes instance, and we can just follow that Hamiltonian circuit, and we know that every edge along that circuit is going to have a cost of 1, which means that the cost of the optimal tour over here is no greater than n, right? Than the number of edges. In this case, it's no greater than 4, right? There is a tour of this graph with a cost no greater than 4. Okay, so let's copy this down. So if G has a Hamiltonian circuit, like this one does, in other words, if G is a yes instance of the Hamiltonian circuit problem, then the optimal solution of TSP, then the optimal, we'll call it the optimal tour in G prime, has a cost less than or equal to n. right? We just follow the Hamiltonian circuit in this graph, and because of our problem reduction, we know that each of those edges have a cost of 1. Each of the edges in any Hamiltonian circuit have a cost of 1. Okay, because all of those edges, existed in the original graph. Okay, so it has a cost less than or equal to 1. And so then, suppose I have a C approximation for the TSP, then that C approximation will return a cost less than or equal to C times n. Okay, so if I have a C approximation for TSP, what can I say about that? Well, the optimal cost is n, right? Is less than or equal to n, actually. And a C approximation always returns an answer that's within a cost, within a factor of C, right? So then this algorithm, this hypothetical C approximation, would return a tour with a cost less than or equal to C times n. Okay. So that's settled, right? That's the definition of a C approximation. Okay, so now what do I know? Well, I know that suppose I have an instance of the Hamiltonian circuit problem that's big, so I can't solve it fast. Well, then what this is claiming is that I could just convert it to this problem, convert it to a TSP, use my C approximation algorithm, and then if the C approximation algorithm gives me an answer that's less than or equal to Cn, then I know that my original problem is a yes instance. Okay, and so then I don't have to do any kind of conversions back, right? I do the conversion this way, solve this thing, get an approximate answer that's with a cost less than or equal to C times n. I know what C is because I know I have a C approximation. I know what n is because I know, there's n nodes in the graph. Then that would let me say this is a yes instance of the original problem. Okay, so now what we have is we could use this hypothetical C approximation to identify yes instances of an NP-complete problem. Right? That looks like we're solving an NP-complete problem in polynomial time. Okay, and where's the polynomial come from? Well, the conversion is polynomial time. It's linear time, right? It's linear in the size of this graph. And then the C approximation is defined as an approximation algorithm, which in all interesting cases is a polynomial time algorithm. Okay, so to complete this, what do we need to do? Well, we need to show that our C approximation could also identify no instances. Because if it ever misclassifies a yes instance, misclassifies a no instance of this problem as a yes instance, then it's not solving the Hamiltonian circuit problem, right? So what happens if we feed a no instance of the Hamiltonian circuit problem into our reduction? Well, let's do this. So we've got now a second G, right? So this is a no instance, and we'll define our G prime, our corresponding G prime. So I'll just use the same one that I did earlier. Right? So here's our no instance. So being a no instance means that there's no Hamiltonian circuit. Okay? So our G prime then looks like this. So every edge that did exist in the original one has a cost of 1, and every edge that doesn't has a cost of C times n plus 1. All right, so if this graph does not have a Hamiltonian circuit, then there's no way to traverse this graph using only edges that have a cost of 1. Right? So that's fundamental by the way we've reduced the problems, right? So if there's no Hamiltonian circuit here, then there's no way to traverse this graph. There's no Hamiltonian circuit over here that uses only edges with a cost of 1, right? What we're saying over here, when we say there's no Hamiltonian circuit, is that the only way to create a Hamiltonian circuit is to add a new edge. Okay, adding a new edge can be done over here, and the way that's done is we have to follow at least one of these Cn plus 1 edges. So okay, so if G has no Hamiltonian circuit, let's write this down. G has no Hamiltonian circuit. What does this tell us? Well, then the optimal solution over here has to use at least one of these expensive edges. Then opt solution of G prime uses at least one expensive edge, right? One Cn plus one cost edge. Okay, so what does that mean? It means that the optimal solution has a cost of at least Cn plus 1. The whole, we know that it has to use at least one of those edges, so that the cost has to be at least this. Okay, so then what happens? So if I have a C approximation for the TSP, then on this instance, it would return a cost greater than or equal to Cn plus 1. And it could be much greater than that, right? It could have multiple of these edges, multiple of these high cost edges, in which case it would be much higher. But the point is that we can verifiably say it's greater than the cost that it would return on a yes instance, or on a graph derived from a yes instance. Okay, so how do we write this? So if I have, this is just analogous to above, if I have a C approximation for TSP, it would return a tour with a cost at least Cn plus 1. Right? Because I know that every tour, every Hamiltonian circuit of the graph G prime has a cost at least Cn plus 1, because it has to use at least one of those high cost edges, right? Okay, so now how do I solve the Hamiltonian circuit in polynomial time? Well, I take my instance of the Hamiltonian circuit, I convert it to an instance of the TSP, I use my hypothetical C approximation algorithm on that instance. If it gives me an answer that's less than or equal to Cn plus 1, then I know that the original instance was a yes instance. The original Hamiltonian circuit problem was a yes instance. If it gives me an answer with a cost greater than or equal to Cn plus 1, then I know my original instance was a no instance. Okay, and so and that allows me to solve the Hamiltonian circuit problem in polynomial time. Therefore, P would equal NP. Right? So then we can reverse the entire thing and say, let's form the contrapositive of this and say that what we've just shown is that if P does not equal NP, as we suspect, then this algorithm, this C approximation algorithm, must not exist. Okay, so here's the statement: is that if NP complete problems are hard, then TSP is not approximable. Right, then we can implicitly do a search over all possible algorithms and say none of them are C approximations for TSP. Right, then TSP is not approximable. Okay, and then we can save ourselves the effort and the time and the pain of looking for polynomial time algorithms that have performance guarantees for TSP. Okay. So it turns out that's not the end of the story, and that's what we'll spend the rest of the time today talking about, is that there actually are variations on the TSP that, one, are approximable, and two, actually seem to have good algorithms for them, even though we can't, even when we can't guarantee how close the algorithms come to optimal.